This conference will now be recorded.
Hello everyone, let us start with this session. Today this will be the PCIe technology, PCIe protocol demo session. In this we'll be talking about what all aspects will be covered and uh, okay. Basically the training will go for around 6 weeks. Uh, it is a 2 days per week. It's a weekends only training, around 3 to 4 hours on Saturday, 3 to 4 hours on Sunday. The training is actually divided into two aspects, two parts. One is the protocol training, one is the test bench development training. The protocol, the one we are talking about, one we are doing is a protocol training now. And in case you are interested after that, we offer a test bench development training specific to each layer, like the transaction layer, data link layer, physical layer. We have a specific course which is done. Okay. So roughly, if you count the number of hours, 6 into 3.5 hours, roughly it goes around close to 35 to 40 hours overall it goes. That's a very good time for us to understand the PCI protocol in depth. Uh, uh, and okay, yeah, even the test bench development is done in the similar lines. I mean, rather I would say this is uh, total around 25 hours course total in total. uh, this is a test bench development for each layer, for individual, for PCIe layers. The course prerequisite. Let's talk about the course prerequisites. Basically, the participants are expected to have understanding of one VLSI protocol. Like it could be SPI, it could be I2C, it could be APB, AXI. Any one protocol understanding you should have, basic understanding. Uh, when we say at least one protocol knowledge, what you should know basic meaning of what is meant by a master, what is meant by a slave, what is meant by a transaction. When we say timing diagram, what exactly is a timing diagram, and protocol signals, how to understand the protocol signal. Let's say in SPI, what is clock, what is chip select, what is address, what is data. That basic idea you should have. Without any protocol understanding, you shouldn't start learning PCI Express. If you don't know any of these protocols and this is the first protocol you are learning, then this is not the right course for you. Then what is covered and what is not covered? What is covered course will be majorly protocol training focused. The first aspect, as I said, the first aspect is only protocol training focused. Like people ask, do you develop any test bench? I mean, if you try to do too many things, the course will not be good in anything, right? Because we focus only on protocol. We'll majorly focus on PCI Gen 3 and Gen 4 protocols. Then we'll also focus on Gen 4 also, actually. Not just final session, we'll focus on Gen 3 and Gen 4. And we'll talk about the PCIe 5, that is nothing but pipe. Then we'll just talk about PCIe controller test plan. What kind of test cases, what are the features, what kind of test cases we can develop. And we'll just take a look at PCIe controller test bench architecture. Then introduction to the PCI Express VIP. I mean, basic idea of VIP, okay. Coding also, let me not say. Let's make it very clear. Basic introduction to PCI VIP integration into test bench. Test bench development. Test bench development. So this is what is basically covered as part of the course. Now, what is not covered? Let's understand. We will not be doing any test bench coding for any of the components. I mean, as part of the protocol training. But if you go to this part of the course, second part of the course, we will be developing entirely everything from scratch. Okay, I wanted to tell you that basically do not mix this and these two. These two are two different courses. Okay, I think that might be sufficient. What is the material shared? We'll be sharing the PCI specification. I'll be maintaining a session notes for each session, and that will be shared with you. And we'll also share some assignments and interview focused questions. And okay, this The presentation access you will get. This is all the material access you'll get as part of the course. Now, what is all that is covered as part of the course? Basically, we'll be starting from the basics of PCI Express, how the PCI Express has evolved, why we need PCI Express, and then we'll be talking about PCI Express topology, I mean how the PCI Express based system look like, and we'll be talking about the concept of configuration headers, configuration header overview, headers, PCI Express topology. Instead of calling as architecture, we call it as PCI Express topology. Then we'll be talking about enumeration, then how the address space and transaction routing happens. Then we'll be talking about individual layers, where we'll talk about transaction layer, the different aspects of transaction layer, the different aspects of data link layer, the different aspects of physical layer, both from a logical layer perspective as well as from an electrical layer perspective. And link initialization training automatically becomes part of this only. There may not be any separate. Okay, these things. Once we are done with that, we'll be talking about miscellaneous PCI aspects, like how the interrupt is supported in PCI Express, how the error detection and error handling happens, what are the different types of errors, and how do we do the error recovery, error detection and error recovery. Instead of saying handling, we call it as error recovery. Some error happens, how do you recover out of that error? Then the concept of power management. Basically, PCI Express has to provide a very efficient power behavior. I mean, if it is not functioning, it should be into a low power state. So how do we do that power management is what we talk about. Then finally, we talk about pipe architecture. Pipe is the PCIe 5 architecture. So this is all what is planned as part of the PCIe protocol training. I won't say technology, so that's a very big keyword. I would even call it as here also PCIe protocol only, not a technology. So let's start off with the PCIe protocol overview. Okay. Initially, to say, though we said 6 weeks, 3-4 hours, my agenda would be whenever it is completed. It could take 30 hours, 35 hours, 40 hours. In a slow, effective manner, we'll be doing. I won't be counting the hours. I won't be even be counting the weeks. Whenever it is done properly, that is when course will complete. Okay. So let us now start with the PCIe protocol overview. First, uh, why do we need a PCI protocol? First, let's try to understand what is the need for. Someone tell me, based on your prior understanding or any exposure to other protocols, why do we need a PCI protocol?
To interact with any different IP.
Okay, any different IP. Okay, see, thank you for that. So basically, PCIe, even though nowhere it's stated, it stands for Peripheral Component Interconnect Express. Peripheral Component Interconnect. What is peripheral component means? What do you understand from peripheral component? What is peripheral? If I take my laptop, what is a peripheral for my laptop? For
Uh,
a
Maybe
laptop,
keyboard or
USB,
USB port.
yeah,
The one which is
mouse.
connected externally.
what is connect? Anything that is connected externally, right? Anything that is connected externally is all called as peripherals. If you go back maybe 2 decades back, around 2000 time frame, when I purchased the desktop at that time, the desktop didn't had one common port actually. Desktop used to have the desktop CPU used to have different ports, one RS232 port for connecting one type of thing. Different ports, different technologies were there, and other. Give a minute.
This conference will now be recorded.
Basically back then, to connect various peripherals, when you say peripherals, that used to be like some floppy drive, the mouse, the keyboard, different types of peripherals used to be there, some graphics card, various things used to be there. To connect them, other protocols were used. RS32, 232, and some other protocols were used. These protocols, so what is the problem here is they had some issues in terms of they were not hot pluggable. Hot pluggable means what? You uh, to connect any of those peripherals into the system, you have to restart the system. Only then it would detect the devices. So they had some little issues, and even they had limitation in terms of the bandwidth that you can get out of it. Right now we are talking about gigabytes per second, right? Some for 60, 50 gigabytes per second or 100 gigabytes per second right now. Back then it used to be like we used to talk in terms of megabytes per second. That used to be the limitation with the protocol that were used back 2 decades back. So there was a need for standardizing the peripheral component interconnection. There was a need for standardizing the peripheral connections. Means what is meant by standardizing? One interface through which you will be able to connect everything, one kind of protocol. That is where two protocols evolved. One is USB, which is universal serial bus. One is peripheral component interconnect. So there evolved one protocol called as PCI. It's not PCI Express, understand? It is PCI, which is nothing but peripheral component interconnect without express. Now you may say, is PCI same as PCI Express? No, both of them are significantly different. Okay, that is where they standardized the concept of connecting all the peripherals. Basically, it's like it is an interconnect. You see, it's an interconnect. Interconnect means what? Some kind of system bar, an interconnect bar to which you connect various peripherals into that port. Okay. This is what this PCA used to connect. And to the same thing, we would connect the processor, graphics subsystem, various memories, everything can be connected to peripheral component interconnect. Okay, the problem, it had its own problems. I mean, initially when they started using peripheral component interconnect, it was good, but later at one point of time it has its own limitations. The limitations are majorly due to one important thing, that is PCI is a parallel communication protocol. Parallel, rather, I would say, what I would say is parallel is like is more like a similar to on chip communication protocol, even though the name is peripheral. But it was what is that makes it parallel is what is meant by parallel here. What is meant by parallel and what is serial? Let's try to understand. And what is the problem with? So let's try to address these questions. What is meant by parallel? What is serial? And what is issue with parallel protocol? First, let's answer the first question. Parallel means a protocol where address, data, and other control information is sent at same edge of the clock. They are sent in parallel, like at same edge of the clock. You would send the address information, you would send the data information, you would send the write read, or maybe in the two consecutive clock cycles. Okay, if you send all the information at same time, then you are sending the information parallelly. We are sending information parallelly, concurrently, right? Or parallelly, because we are using the term parallel. Okay, that makes it parallel protocol. Then what is serial? What is serial protocol? Protocol where address, data, and other control information sent at consecutive clock edges. With few bits sent at a time. Serial manner, basically. You don't send all the information at the same time. You would send one bit, the next bit, at the next clock edge, next bit, so on. That would make it serial protocol, right? At first look, this looks more efficient. I mean, initially, if you see, uh, from a I mean, without going into the deep depth of the protocol behavior and other things, parallel protocol looks more efficient, because if parallel protocol is sending 32 bits parallelly, if parallel protocol is using 32-bit interface, and serial is using 1 bit interface, 1 bit data interface, data port, data pin. So it looks like parallel is 32 times more efficient than serial protocol, right? Because whatever in one clock, if you can send 1 bit information using serial, using parallel you can send 32 bits at the same time. But then it has got its own limitations. See, parallel protocol has its own limitations. Even though here it looks better, but parallel protocols are always limited by parallel protocols. What are the examples of parallel protocols? AXI, HB, APB, OCP, Wishbone. There are many protocols. These are all limited by frequency of operation. Now the question comes, why they are limited by frequency of operation. Let's try to understand why they are limited by frequency. See, frequency is decided based on timing closure. I mean, once a chip is manufactured, you need to during the chip manufacturing, there is an important step called as static timing analysis, where we do the setup and hold time analysis. It is important to make sure that there is no setup and hold time violations during this entire VLSI design flow. I mean, it could be during physical design or even during after the place and route, anything. There should not be any setup and hold time violations. As you increase the frequency, as we increase the frequency of operation, let's say you take a chip, one point of frequency is, let's say, 2 gigahertz. Other point of the frequency is, let's say, 4 gigahertz. Let's take an example. Here, the time period will be 5 nanoseconds. Here, the time period will be 2.5 nanoseconds. So that means what? As you increase the frequency of operation, the time period of that clock comes down. What is it has to do with the setup time? Let's try to understand. In one case, my clock will look like this. In the 2 gigahertz case, my clock will be like this. This is 5 nanoseconds. In another case, the clock will look something like this. This is 2.5 nanoseconds. Now, what is that? Again, it has to do with the setup and hold time. See how it has to do with setup and hold time is, typically, if you take any circuit, it will be like this. There will be a flip-flop. There will be a flip-flop. In between, combination logic will be there. The output of this becomes input to the next flip-flop. They have to eventually meet the setup time. The time at which it reaches this point has to meet the setup time with respect to this clock. As you increase the frequency, what happens is the amount of time it requires to travel here comes down, because I need to reach, if this launches the data here, it has only this much time to meet the setup time. Whereas in the first case, it has got more time. You see, it has got more time starting from here till here. This much time it has to reach here. So because of that, as you increase the frequency, the difficulty in meeting the setup time increases. So hence, that problem is one thing is there. Okay. Now you may say, won't this problem be there in peripheral protocols? It won't be there. We'll discuss that part. Uh, this problem is majorly coming because uh, this is coming majorly because the clock is sent as a separate signal. Whereas in peripheral protocols, what we do is, in the peripheral protocols, that is in the serial protocols, high speed protocols, the clock is not sent separately. clock is extracted, clock recovery happens from the data pattern itself, from the data pattern. So because of that, there is no need to meet setup and hold time. I mean, there is no reference for you. I mean, there is no reference for you. Basically, the receiving circuits just sees the toggles of the data and it captures the data. Whereas in AXI protocol, for it a clock edge is the reference. Okay. Whereas in peripheral protocols, there is a clock recovery circuit which uses the incoming data pattern itself to recover the clock. So both of them are anyway synchronized. That issue with the setup and hold time doesn't arise. The second problem that happens in parallel protocols is one is issue with the setup time and hold time. Okay. The second issue is with, this is the first issue. The second issue is with the skew, clock skew, serial protocols. Sorry, not serial, parallel protocols. In parallel protocols, what happens is uh, clock is sent. See, if you look at AXA protocol, there is a dedicated clock signal. In AXA protocol, there is a clock signal in the frequency. In AHB also, H clock is there. In APB also, P clock is there. Any protocol you take, there will be a dedicated clock signal in case of parallel protocols. So the clock is also going, data is also going parallel. So there is always a chance of skew getting developed. Means this is the clock signal, this is the address and data signals. Though I'm not toggling, it is toggling. Okay, there is a because this is one block, this another block, there's always a problem with this information reaching at different timings here. This may reach bit early, this may reach bit late, this may reach bit between. So now the point comes, when will I sample? If I sample here, I will sample this properly, but I may miss sampling out this one. Right, as you increase the frequency, this becomes more and more problematic, because as the time period reduces, this will have more impact, right? The difference will have more impact. It's like simple saying that there are 5 people running 100 meters race. 1 2 3, all of them reach at the same time? No, right? They will differ by few units, some meters or some nanoseconds. The same problem happens where signals are launched at same time. Due to the wire behavior, copper wire behavior here, they may reach this point at little variations. That differentiation is called as skew. It is called as skew. Now since clock is also coming separately, it becomes difficult to at times, due to this skew, we may not be able to sample the signals properly. And if you sample something different, I mean, not in a proper manner, you will get a wrong data. That problem won't be there in serial protocols because there is no clock at all. You don't transmit the clock. You will embed the clock. Whatever data pattern you are sending, in that itself, the clock gets embedded. The receiving side, it will using this data pattern toggles. When it is toggling high 1 to 0, 0 to 1, it knows what is the clock frequency and it extracts the clock from that. So what is that? How do serial protocols solve the problem of the clock skew? How serial protocols? Serial means high speed serial protocols, I would say. High speed serial protocols solve the clock skew problem. Basically, eliminate clock transmission itself. Don't transmit the clock from transmitter to receiver. No clock from transmitter to receiver. Then there is no question of skew itself, right? If there is no clock, then there is no skew. Then without clock, the question comes, without clock, how can you collect the data? Without clock, how can receiver collect the data? It has got a clock recovery circuit. Receiver is a complex clock recovery circuit, which extracts the clock from the incoming data bits itself, incoming data bits toggling. As the incoming data bits are toggling, from there itself it extracts the clock. So majorly these were the two problems. One is the meeting the setup time requirements. One is the problem with the clock skew. There will be one more thing called as flight time. It is all related to the same thing, clock time period only. Okay. Uh, with this understanding, let us now go into the protocol and try to understand. So before we move on to the PCI protocol, I think let's talk about some of the protocol basics. See, what is a protocol? A protocol is basically a guideline on how the transfer happens between a one component to other component. It could be master to slave, it could be transmitter to receiver. How the information is exchanged between one component to other component, that guidelines is collectively called as a protocol. Typically, if you talk about any protocol, you will come across information like various phases that protocol implements is arbitration phase, address phase, data phase, response phase. Some protocols may have arbitration, some protocols may not have, but this how majorly any protocol communication can be divided. It's a guidelines on how various phases happen. Protocol also provides signals to implement these phases, like AXA protocol provides AW address, AW length, AW size. APB has a different set of signal. Basically, the company which provides the protocol, they will tell the guidelines on how the communication happens. They will also provide the detailed signal description, what should be used for what. Protocols are majorly two categories. One is on chip, one is peripheral. On chip examples are these things: AXI, HB, OCP, PCI. Even PCI is a on chip protocol, whereas PCI Express is peripheral. On chip protocols are limited by frequency of operation, we have discussed, because as you increase the frequency, the time period comes down, which makes it difficult to meet the setup time. That is why when you purchase a mobile phone, the mobile phone maximum comes out at 3 gigahertz. Probably you may not have even purchased a mobile phone which works beyond 3 gigahertz, because once the same mobile phone, the one which is in my hand, I could even run it at 5 gigahertz. But the problem is it won't be stable. It won't work at all, because as soon as I use a crystal in my mobile phone which is giving 5 gigahertz clock, mobile phone becomes immediately unstable, because it will have setup violations at every point in the mobile phone. So there it will go into unstable state, because that is where they will define that this mobile phone will only work at 2.2 gigahertz, because that is where they have done the static timing analysis, setup and hold time closure. Now, as I said, that limitation won't be there in peripheral protocol, because you don't send the clock. There is no reference. I mean, reference clock itself is derived from the data pattern. Hence, there is no problem of setup and hold time violation there. What is the other thing about on-chip protocol? Data communication happens in terms of transactions, like AXA transaction, APB transaction. You use the term transaction. And on-chip protocol uses various phases like arbitration phase, request phase, data phase, and response phase. And handshaking happens using a dedicated signals. In case of AXI, we use valid and ready handshaking. In case of AHB, we use trans and ready handshaking. Whereas in peripheral protocols, what are the examples? USB, PCI Express, SATA, even SPI is an example of peripheral protocol, I2C, UART. Peripheral protocols are limited by number of ports, because peripheral protocols are always coming to the periphery of my electronic system. So we want peripheral to be as small as possible, right? So that is where they are limited by the number of ports. As you increase the number of ports, what will happen? My port size will increase significantly. That is where you see USB has only 8 pins or 9 pins. SD card will only have 8 pins. Everything is, even Ethernet has only 10 pins. Everything has limited number of pins. Whereas in case of on-chip, there is no such limitation. The on-chip fabrication technology is so advanced that inside the chip, I can manufacture 100 wires in 1 micrometer. In 1 micrometer, I can place 100 parallel wires. That I cannot do. If you imagine 1 micrometer, I can only hardly place one wire only outside. In case of peripheral, data communication happen in terms of packets or frames. Handshaking happens using a preamble and sync. There is no dedicated signal for handshaking purpose in peripheral. It all happens using some packet called as preamble or sync packet. Receiving device uses preamble or sync pattern to detect the start of packet. To detect when the packet is starting, the receiving device uses preamble and sync patterns. Now, talking about these protocols, how do we differentiate the protocols? Protocols are differentiated based on the performance. What is the performance you get out of the protocol? What is meant by performance? How much bandwidth do you get? How much gigabytes of transfer happen per second, or how much megabyte transfer happen per second. That is how you say this is a high performance protocol, this is a low performance protocol. Then the amount of power consumption that involves. Then the how many features are supported. Let's say, why do I say that AXI is a better protocol compared to APB? Because it supports more features like wrapping, incrementing, cacheable, bufferable, out of order, overlapping. Many features it supports. Because of that, we say that AXI protocol is better than, has more features than APB. Then finally, pin count. How many pins it is using to implement? Because as you reduce the pin count, it also reduces the size and it reduces the cost also to one extent. So what is the ideal behavior we are looking at? We want high performance. We want a reduced power consumption. The feature should be higher side. Pin count should be lesser. That is what we want basically. But thing is, generally speaking, you can't get best of everything. I mean, somewhere you have to compromise. What is that PCI Express does is, it tries to get you best of everything. I mean, not that it cannot give you best of everything. What does it mean? You may be thinking he's conflicting again himself. Mean you can't have a topmost performance and it cannot run with a zero power consumption. It needs to have a power consumption. It needs to have a some pin count. Only then it gives the performance, right? So, but it gives you the optimal performance, where you have optimal performance at a relatively lower power consumption with maximum number of features supported and with minimal pin count. That is what PCI Express gives. What are the advantages of on-chip protocol? See, advantages are all signal communication are done concurrently. Like what example? AW address, AW burst, AW size, all information can be given in one clock edge only. Fabrication technology allows implementing hundreds of signals in very narrow space. Like in 10 micrometer, we can route complete AXI interface signals. Since protocols have many signals, we can implement various features like overlapping, out of order, cacheable. Because it has got many signals, it gives me flexibility to implement all the features easily. What are the drawbacks with on-chip protocols? They are limited by frequency of operation. I told you, right? As you increase the frequency, the time period comes down and it becomes difficult to meet the setup time. Let's say you take an example of a Qualcomm Snapdragon based mobile. Okay. Okay, it will come with specification that processors will work only at 2.5 gigahertz. I mean, if one of the processor if you purchase, they will say 2.5. Reason is the timing closure. A chip consists of lakhs of flip-flops. One register is nothing but 32-bit storage. 32-bit storage is nothing but 32 flip-flops. Thousands of registers means lakhs of flip-flops. Okay, every flip-flop has setup time and hold time requirement. For every setup, every flip-flop, there is a setup time and hold time we need to meet. If we violate this timing requirement, setup and hold time, flip-flop enters into metastability state. When it enters into metastability state, output of flip-flop can be either 1 or 0. This metastability spreads to the whole chip since everything is interconnected and whole chip enters metastable state. I mean, even if one flip-flop enters into metastable state out of 1 lakh, then finally, eventually, whole chip enters into metastable state. Okay, that is one of the major drawback. Second drawback is it requires many ports for master to slave connection. You need to do many ports, right? That also makes the things complex. These are the major two drawbacks. And other thing was the skew. Skew was anyway we discussed. Yeah, skew was the other problem. Skew means what? Signals arriving at same port with varying delays. Different signals are coming from master to slave. Like AW address is coming at one moment, AW length is coming at a different moment. So if different signals arrive at different moments, that gap at which they are coming is called as skew. All the connections between master and slave is a copper wires. If you see, these wires between master and slave can have varying delays. Because these are copper wires, they can have varying delays, right? A skew is a concern in parallel communication protocol, since signals are skew is a concern in parallel communication protocol since all signals are driven parallelly. If they reach at different times, we may sample wrong values. A skew can be two types. One is data skew, varying difference arrival times in the bits of the same signal. Data skew means what? Varying difference. Let's say data is coming as 32 bits. Data 0 is coming at one time, data 31 is coming at little late time. So there can be a data skew. Clock skew means what? the varying difference of arrival time in different ports with respect to the clock edge. The clock skew means what? With respect to the clock, how signals are coming. Data skew means what? Internal to the data, how the signals are reaching. Eventually, both of them are bad. Not like one is good, one is bad. Both of them are bad for the protocol behavior. Skew is always bad actually because it always limits the frequency of operation. And lot of because it limits the frequency of operation, it limits the bandwidth. That is where even today, after 50 years of electronics industry, right, or whatever, how many so many decades of electronic industry, we are not able to operate mobile phone kind of complex devices at 5 gigahertz or even 4 gigahertz. You wouldn't hear because skew is one problem, the timing closure is other problem. All these problems is resolved in the parallel communication protocol because there is no need to concern about the setup and hold time there, because there is no clock uh, being transmitted, there is no concept of skew. Then you may say, yes, what about data skew? Data skew can still be there, right? If you are sending 4 parallel wires, they have a mechanism called as d-skew. D-skew means what? Something that fix the skew is called as d-skew. The data skew is there in PCI Express also. But to fix that, they use a mechanism called as d-skew. But you won't see the clock skew. Why clock skew you won't see? Because you don't transmit the clock. If you don't transmit the clock, there is no clock skew. There is no setup and hold time violation because you don't again generate the clock. There is a clock that is being generated, which is using the data itself to generate. Then automatically timing, the sampling is happening properly. It is all the magic of the complex analog circuitry what makes this high speed protocols possible. Next, let us talk about peripheral protocol overview. See, peripheral protocol communication or data happens at the chip boundary. That's why they're called as peripheral protocols. We need minimal number of wires so that their size can be smaller. Like USB 4 has 4 wires. Imagine USB having 20 wires. The USB port would have been 5 times bigger, right? USB port size will increase, and then my laptop size also has to increase automatically. What are the advantages of peripheral protocols? It uses less number of pins. What is the advantage? Reduces the port size, limit the number of ports. Other major advantages, very important advantages, it can work at very high frequencies. Since clock is embedded into the data pattern, there is no question of setup or hold time violations. Hence, it can work at any speed. Since even now we are talking about what speeds? 60 PCI Express Gen 6, we are talking about 64 gigatransfers per second. That is nothing but 64 gigahertz roughly. Since queue won't be a problem, since information is sent in serial manner, can result in very high bandwidth. Because we are able to operate at very high frequency, it translates into higher bandwidth. What are the drawbacks? PCI and these kind of high-speed communication protocols requires a complex PHY logic. I mean, requires a complex analog circuitry, what we call as PHY, which increases the chip complexity and the cost. I mean, that is something you cannot avoid, because if you want something better, you need to have a complex circuitry, right? That is what we are talking about. That I cannot even say drawback actually. Essentially, high-speed peripheral protocol, I would say there is no drawback except for the complexity of the analog circuitry. Now, protocol differentiation with so many things. How do you differentiate protocols? As a device developer, let's say I'm developing a device. What is meant by device? I'm manufacturing my music player or a pen drive. I want to decide that which protocol should I use. I want to choose a protocol for my device interfacing, because once I manufacture a device, let's say this is my device, how do I connect to the laptop? I need to give some interface through which I insert it into it and connect it, right? So how do I choose which interface should I use? So as a manufacturing, let's say I'm manufacturing the printer. So first thing what I will do, I'll see to which systems it needs to connect. Printer needs to connect with systems like personal computers and laptops. As a manufacturer, which protocol is best suited for me? That's what my question is. What factors do I consider for a printer? I need to make sure that my protocol should give me the required performance requirements. Means bandwidth should be met, right? It's not like I'm giving a paper printout and it's taking 1 hour to print it, because it works at a low bandwidth. Then it won't be good. and it should work at a low power consumption. It should not like printer should get heated up in 1 minute. Okay, it should be low cost. It should have a lower minimal circuit complexity, as much low complexity, and it should be peripheral connection, right? Because I cannot insert printer into my laptop, so it has to be a peripheral connection. So here we classify, so the protocol based on how they give above parameters. See, no protocol can give best of everything. Okay, we can get few of them best, so other place you have to compromise, right? If you go for very high performance and high power consumption, you have to compromise at the cost. It's like Intel and AMD processor. Intel gives the best performance and better power consumption. You have to pay a higher cost. In AMD, it doesn't give so much better power consumption, right? So that is the same relation here. Okay. PCI gives you 3 positives and 1 negative. What is the positives it gives you? It gives you very high power performance. It gives you decent power consumption, and complex circuitry will be there, but cost will be higher side because the manufacturing involves a complex circuitry. Okay, how does it give high performance? If you take a X32 device, let's say, I mean, what is the performance you can expect out of PCIe Gen 4? Let's understand. Performance we can get with PCIe Gen 4. Let's say Gen 4 supports link with width of X1 to X32. X32 means 32 lanes per link. Is what we call as X32. X1 means only one lane per link. You may say, don't think that this is one statement. This is one type of link. This is another type of link. There can be link with one lane only. There can be a link with 4 lanes only. What is meant by lane here is, I have a device here. I have another device here. If I say link with one lane means there's only one transmitting line. There's only one receiving line. This makes it one lane. If I say 32 lanes means there will be 32 transmit lines and 32 receive lines concurrent. So there will be such totally 32 lines will be there. There will be similarly 32 receive lines will be there. That is what makes it X32. Okay, tell me which one will give me better performance, X1 or X32? X32 will give you better performance, and of course the factor is 32 times, because if one lane can carry some data, 32 lanes can carry 32 times more data. Okay, now so to get the highest performance, which one should we use, X1 or X32? X32 will use. So Gen 4 can work at 32 gigatranspers per second. Gen 4 works at 32 gigatranspers per second. Gigatranspers per second means in 1 second it can transfer those many bits, 32 gigabits it can transfer in 1 second. So what is the overall bandwidth we get out of it? See, 32 gigatransfers per second into 32 lanes, right? Because you can use 32 lanes, and you see it can do both transmit and receive. See, when you measure the bandwidth, you don't measure just the uploading bandwidth. You measure both upload and download bandwidth. Mean your bandwidth is addition of transmit plus receive. How much you can transmit, how much you can receive into 2. If you see, what does it come to? 32 into 32 is 1024. 1024 into 2 is 2048 gigabits per second. You just do the multiplication, it will come to gigabits because it is 32 bits. And 2 is for what? Transmit and receive. If you convert to bytes, what does it come to? Divide by 8. 256 gigabytes per second. This much bandwidth you can get out of PCIe Gen 4. Okay. Now, what about PCIe Gen 5? Everything else is same. Only thing is it can work at PCIe Gen 4 can work at 64 gigatransfers per second. The frequency, the speed is doubled. So naturally, this will double to 512. Just imagine that's a very big number actually. 4096. That's a very big number. So it will come to 512 gigabytes per second. You can imagine how much speed it will be. But in real life, we don't use X32. Nowhere X32 is used. Protocol says X32, but the best anyone has used would have used is X60. So this is theoretical maximum that's possible, but when you use x16, naturally it comes down to 128 and 256. So that is the same calculation you can see. Okay. 2 terabits per second is theoretically possible. Generally, we don't calculate in bits, we calculate in bytes. This many gigabytes per second or megabytes per second. Okay. So what AXA can give? So this is what PCI Express can give. What AXA would have given you? AXA is among the top on-chip protocols. AXI, ACE, these kind of protocols are on the top. AXI 32 data bit width and 2.5 gigahertz is the clock frequency, which is 75 gigabits per second. Let's say instead of 32-bit, let's say if I use 64-bit data width, that AXI data bus width can be 64, let's say. 64 into 2.5, maximum you can get is 150 gigabits per second, whereas PCI can give you 2048 gigabits per second. That is where PCI gives you so much high performance. And what is meant by reasonable power consumption? PCI Express implement power saving features which significantly reduce the power consumption. I mean, whenever there is no active packet transmission, it can enter into a low power state. And once the packet transmission starts, it comes to the normal operating state. And relatively higher cost. Okay. Basically, cost will be higher because of the complex circuitry. Then it provides lot of features. What is meant by lot of features? We'll discuss in the following slides. So that means what AXI based systems can work maximum at 2.5 to 3 gigahertz due to the timing closure requirement. They can give this much bandwidth only at max 150 gigabits per second. Whereas if you convert it into bytes, it comes to some 20 around 17 gigabytes per second. Okay, so this is how you differentiate the protocol, and this is where I may choose that I will go with PCI Express protocol for implementing my device interface because I get this much high bandwidth by using PCI Express, and I get to use lot of features, and the power consumption will also be will have a reasonable power consumption behavior, and I'll have a lot of features that can be implemented. Okay. Next. PCI Express is a universal protocol. Is a truly a universal protocol because why it's universal protocol is it supports all the major features of every other protocol. In AXI, let's say you talk about out of order transaction. PCI Express supports out of order transaction. Cacheable transactions. AXI supports cacheable transaction. That concept of cacheability is there in PCI Express also. So any feature, major part of the features that are supported in any other protocol are all there in PCI Express. Okay, let's say posted writes, non-posted writes. You can call there is some posted write and non-posted writes in OCP protocol. They are there in PCI Express also. So all the important features that are present in any protocol, they are all kept into PCIe. That's why we are calling it as a universal protocol. By learning PCI Express protocol, you get versed with all the major features. So automatically enables you to learn all other protocols because you get exposed to each and every feature, how it works. There's a concept of snoop, there's a concept of out of order transactions, there's a concept of arbitration. Everything is there in PCI Express. uh, Further talking about protocol differentiation, AXI, if you take AXI, we use AW burst to do fixed wrapping and incrementing transfer. I mean, though I may be using AXI, if even if you don't think that should I know AXI to learn PCI Express, no, I'm just using AXI as a reference to teach the PCI Express protocol. Okay, this will be only for this 1 hour only. Once we are done with this 1 hour, I won't be even talking about AXI protocol. It is just for comparison purpose. I'm using AXI. So what is that I'm trying to tell here is to implement different features in AXI, we use different signals. We use more signals because we need to implement different features. Like to support fixed wrapping and incrementing transfers, we use AW burst. To support normal locked and exclusive, we use AW lock. As we add more signals, we start implementing more features. I mean, to implement more features, we need more signals. So AXI is implementing features since it has got more signals sent from master to slave. Whereas in PCI Express, we don't have that flexibility. PCI don't have any ports like AX and HBT. It has to do everything through limited number of pins only. So everything happens on 2 lanes only. One transmit lane, one receive lane. I'm talking about a X1 link in case of X1 link. Let me just cross one link. Uh, as we add more signals to implement more features, XI implement features by adding more signals. Sorry. But the problem is in PCI Express, we don't have that flexibility to add more signals. I mean, the number of lanes are always limited. If it is X1 means one transmit lane, one receive lane. Then how do we do that? If we have to do in only one lane, how can you tell that I want to do fixed transaction or I want to do normal, if at all? How do you do that? Everything is done by means of packets. Okay, we'll discuss that part now. If PCIe don't have dedicated signal, the question is in AXI we had a dedicated signal called as AW bus through which you will tell I want to do fixed transfer, I want to do wrapping transfer, I want to do incrementing transfer. For lock also there is a dedicated signal. In PCI Express you don't have dedicated signal. Then without having dedicated signal, how PCI Express implements all the features, how it implements different features. So that is where PCI Express uses something called as transaction layer packet header, transaction layer packet header, where all the fields will be present, which will indicate what is the all the information about the this header fields. Down same thing in explain. Every TLP has a header that is called as TLP header, which is three double words or four double words, three double words, three or four double words, which is nothing but 46 bits to 128 bits per header. Means one double word is in all our terminology going forward for next 6 weeks. Whenever we use the double word, means double word or DW, it means 32 bits. These 96 or 128 bits are used to implement various features of the protocol. Using that, you will tell out of this 96 bits, you will tell using 2 bits, you will tell you I want to do out of order transaction. Using 1 bit, you will tell I want to do snoop transaction. Using 1 bit, you will tell it's a posted write. Using another bit, you will tell it's a write or read. Everything you will tell by using these bits only, because you don't have dedicated signals. Like the way you have dedicated signals in AXL, you don't have. You have only lane through which you have to do. Okay. Now you may say till now you said X32. Even if it is X32, it has to still use the same common lanes to convey all the information. Okay. Through these bits, initiating component indicates all the information about the transaction to the target device. Basically, all the information is kept as part of these double words. Let us talk about parallel and serial communication. What is parallel? Serial communication means. We discussed, right? What is parallel means? Information all going in concurrently is parallel. Serial means what? One bit by one bit going is serial. Now, when I say X32, PCI Express supports X32 lanes, right? Is it parallel or is it serial? No, it is still called a serial only, because 32 bits will go. See, what is parallel? Parallel means address, data, write, read, burst length, everything going at same edge of the clock is parallel. Serial means what? They are going one after other. We are going to X32 only because we want to improve the effective bandwidth. It is still a serial only, even though it is X32, even though data bits are going parallelly, it is still serial, because in the 32 lanes I'm not going to send all the address, all the data, all the write, read, and every information I won't send at one go. They will be sent one after other in the consecutive clock edges. That is why it is still a serial protocol.
Then single lane also it can do. Why we need 32?
32 lanes because you get 32 times bandwidth. If you say using 32 lanes, how much bandwidth you get? 256 gigabytes second. Using the X1 link, what is the bandwidth? You get 8 gigabytes per second.
But here we are running 32 lane, but we are not using the whole bandwidth, right?
Where we are not using?
in 32 lanes. As you said,
No,
it will be serial.
no, not like that. We are using it. See, the information will be sent in a distributed manner. If you want to send, it's like, imagine simple example, difference between x1 and x32. I'll tell you. Example. Let's say there is one room, there's another room. There are, let's say, 1,000 people here. Okay. They want to go from here to here. If I use a lane which can support only one person at a time, let's say each person goes every minute. 1 minute, one person goes. Tell me how many minutes will it take to send 1,000 people? 1,000 minutes. Now I will move to X32, where I'll construct a channel where there are 32 lanes are there like this. Now how many minutes it will take to send? Around 33 minutes. 33 minutes. How the people will go? In the first set, first person, second person, third person, 32nd person. In the next set, 33rd, 34th, 64th person. Like that. Each time 32 people will go. Here only one person will go. Both are called as serial only in this case. Both are called as serial only. What is making, then you may say, AXI, can I call AXI also serial? No. Why AXI is not called as serial is because in AXI, address is sent at same time. Data is also sent at same time. Data is sent in the next cycle, but address, control information, AW length, AR size, everything is sent in one clock cycle. Here it's not like that. First you send one set, next set. That's the point of difference between serial and parallel. Why reason from going to x1 to x32 is because it gives me those many times of performance more. But then in real life we don't use x32 because it's complex and it involves the port size will significantly increase. Actually, imagine this will be x16, x32 will be this much in my laptop itself. Imagine inside my laptop having some port having this much size. It's very difficult to manufacture this. Not only that, 32 is not really 32. 32 is actually 64. Why is it 64?
There are two for one
Transmit and
receive
receive. And 64 is not actually 64, it is 128. Why is 128? It is because this use differential signaling. PCI Express uses differential signaling. What is meant by differential signaling is every signal you transmit, you send it as a differential high signal, differential low signal. That means you have one, if you are using 32 means you actually have 128 wires. If you are using X16 means you have 64 wires actually connecting both. Now that is a complexity, right? That adds to the complexity at the end of the day. That's the reason. But PCI Express, even if it uses X32, it's still called as serial only. How PCI Express has evolved. Okay. Let us take a break. We'll start after some time.
This conference will now be recorded.
Okay. So in this session, let us discuss about how PCI Express has evolved. Okay. I told you that the initial days of peripheral connections were not done using PCI Express because PCI Express is a recent thing that started around 2000s only. Before that, there used to be protocol called as PCI used to be the protocol that was used for connecting all the peripheral components, and that was a standard in itself because that gave one uniform way in which any. What is the advantage of having this uniform standard was that, let's say I am developing one printer, because printer was existing long back also. Okay. Scanner, different things were, right? Pager, different things were there, right? With all those things, fax machines, all those things needed. When I'm developing, I need to have one standard interface where I know that if I develop my printer or scanner or fax machine with one standard interface, I should know that my device also, my laptop or PC will also come with that standard interface. I can connect both of them. So that is where this standardization was very important. That is where PCIe got standardized. But the problem is, at one point it became a limitation in terms of the bandwidth that it can provide. Okay, because now we are talking about high-end graphics applications, the Ethernet. I mean, applications which involve huge amount of data transfer. for which PCI is not the right choice. That is where they have taken the best features of PCIe, they have taken the best features of other protocols, and that's where they came up with PCI Express. So let us now understand how PCI Express has evolved. See, PCI Express has evolved from two protocols, PCI and PCIX. These are three different protocols. Again, PCI is different, PCIX is different, PCIe is different, but this is the most latest protocol. See, PCI stands for Peripheral Component Interconnect, and as I said before, PCI is completely different from PCI Express. What is the need for PCI? I told you, right? Take any computer system to how to summarize computer system, processor and various peripherals connected to each other using the motherboard. There is a motherboard on which everything is connected, right? Basically, all the peripherals are getting eventually connected to the motherboard, right? It requires interconnection of all the components. There was need for protocol which helps with this interconnect. That protocol was PCI. Basically, it is a standardization of connecting all peripherals to the system. PCI, it's a peripheral component interconnect. All computer peripherals connected to the interconnect. PCI specified guidelines for peripheral communication. Like what is the frequency at which PCI works? 33 megahertz. Understand, it's very low frequency. But back 3 decades back, it was a good speed actually. If you go to 1990s, 33 megahertz was a very good speed at that time. So it used to give maximum. I mean, 33 megahertz into 32 bits per second, because data bus used to be 32-bit. You would get 132 megabytes per second. It supports one concept called as full bus mastering. What is full bus mastering is, if I have a system, imagine I have a system like this, where multiple peripherals are there, one component, another component, another component, another component. What is full bus mastering means? Anyone can initiate the transaction to any component without processor intervention. I mean, processor don't need to read and processor don't need to write here. Don't need to read and don't need to write. I can initiate write to this. It can initiate write to this. That all thing can be done. That is what we call as full bus mastering. What is mean by full bus mastering? All components connected to the interconnect can act as masters. Now they can all initiate the transfers without processor intervention. That concept is called as full bus mastering. And what is that really makes it possible is the concept of DMA. PCI has one concept of DMA, PCI interconnect, or topology architecture has a DMA which allows any component on interconnect to behave like a master. Means it can initiate the transfer. Any component can initiate the transfer. Support burst mode also. What is burst mode means? One address space you do, and you do multiple data phases. Allows multiple set of data to be sent. And most important thing about PCI is address and data bus are shared. That way they minimize the pin count. See, when they are sending an address, they will say they will use same pins. To send the data also, they will use same pins. Next, PCI does not have physical layer or file. And one of the limitations, see, these are all the good aspects of the PCI, because it sharing the things, supporting burst mode, full bus mastering, and this much bandwidth. These are all the good things. But what is the problem with PCI is, maximum you can connect 4 to 5 slots. Means here, how many things are connected here? 6. 1, 2, 3, 4, 5, 6. This becomes a problem. Problem is because the load on this interconnect increases. See, if it has to send the information here everywhere, right? The amount of load that is coming to this point to the interconnect in summary is increasing. I mean, I would say it like this. You have an AND gate, output of AND gate is driving multiple gates. As you increase the number of gates here, the load here increases, because I have responsibility of driving lot of other things. So hence the load increases here. The same problem happens here also. So that is where it limits the number of gates that you can connect, number of slots you can connect. Basically, this is limited due to the maximum load it can take. So as the frequency of operation increases, the load, this number of slots also reduces. Okay. So because of that, this becomes a major limitation. Then to support more connections, you have to use something called as expansion slot to connect more peripherals. I mean, what you have to do in that case, you create one more interconnect here. Then here you connect all the peripherals to this. Let's say again you want to connect more. Again you do the expansion slot. Here you connect. Then PCI uses a concept called as arbitration. See, these were all the positives about PCI. This is the negative about the PCI. Okay, means limitation is this one. Then PCI uses a concept called as arbitration. What is arbitration means? Because do you think is it possible with common interconnect? Is it possible for everyone to initiate transaction at same time? Not possible, right? Because there is a limited set of wires only. Same set of wires has to be shared by everyone. That means only one of them can initiate a request at any time. So how do they decide which one to initiate? That is where comes a concept called as arbitration. So they use concept of arbitration. Whichever component wants to access the interconnect, it issues a request. The arbiter which is present inside the interconnect, where is the arbiter present? It is present in the interconnect, will issue the grant. Okay. The PCI device sends request for interconnect. Arbiter gives grant. So the request is through request and the grant interconnect is given grant through GTL. Okay. I think we can write here only. No need of request is IQN. Grant is GNTN. What is small n here? Can you tell me? What is this concept of small n? No, no, no. N means number, right? There can be multiple masters are there. For each one, there is one request signal assigned. So for this request one signal, for this request two, for this request three. Grant one is for this, grant two is for this. That grant will tell who is granted. The limitation is other limitation is it is limited due to the frequency of operation, since it's a parallel communication protocol. Since it's a parallel protocol, you know what are the problems associated with parallel protocols, right? The factors like data skew, all those things will come into picture. Data skew, clock skew, all come into picture. Okay, these are the drawbacks. I think we should have written here as a drawbacks. Arbitration is not a drawback. How it works basically, this is the basic operation of this one. These are the unique features of the PCI protocol. These are the drawbacks. And arbiter sitting in the bridge. Okay, arbiter is part of the interconnect. That's summary. That summarizes everything for us, right? Any questions so far? I hope you understood PCI. If you ask me, do I really need to learn? Do I need to become expert with PCI to learn PCI Express? No. We are just trying to put a foundation to learn the PCI Express. I mean, instead of directly starting with PCI Express transaction layer, data link layer, I'm trying to give you a perspective how PCI Express came to evolve, right? Let us move on to the next slide. So this is about PCI. Basically, what are this is a PCI timing diagram. What is that you can see is there is a AD bus. AD means address and data bus. On the same bus you send the address, on the same bus you send the data. First thing. Okay. That means it's a bidirectional bus. Why it's bidirectional? Because data can be written, data can be read. That means it's a bidirectional bus. Whenever you are sending the information, whole information, during that time frame is asserted. Means during that time this information is valid. Okay, then you send the C and B. There you send bus command, which command you want to do, whether you want to do write or read, and byte enables, which bytes are valid is indicated through byte enable. B stands for byte enable. Then I ready means initiator ready, T ready means target ready, then device selection. These all things will indicate when the data is happening. See, when the device is target is ready, that is when the transfer is happening. When the target is ready, transfer is happening. When the target is ready, transfer is happening. When the initiator is ready, that is giving the information basically. Okay. See here, target was ready but initiator was not ready. So when both of them are ready only, transfer is completed. Okay, this much basic understanding is sufficient. Okay, how many data phases have actually happened? One address phase, three data phases, 1 2 3. That's why it's called as what? burst transfer. You issue address space only once, data space is done multiple times. This is called as burst transfer. Next, what all signals it uses? Clock, frame, address and data bus, initiator ready, target ready, device selection, grant. Address and data bus are shared. What are the limitations in PCI? PCI has limited number of slots due to load limitation at specific frequency. Bridge is a way to increase the number of slots. Not the bridge, another interconnect basically. Clock is sent along with the data, puts limitation on the frequency. It's a parallel protocol where clock is also transmitted. So that puts a limitation on the frequency of operation, and it also introduces the skew. But what are the important concepts that we take from PCI? So see, more importantly, we are not concerned about the negatives. We are concerned about what all positive aspects we can take from the PCI protocol. What features? Let me just write it down here. What features PCI Express takes from PCI? Okay. There are some features PCI Express takes from PCI. Those are these things. Down you can see these features. It uses a process programmed IO, processor programmed IO. Okay. Burst transfers, peer-to-peer communication happens through full bus mastery. Uh, Mostly it uses these features actually. These are the features it takes from the PCI. It uses this concept of PCI configuration space. All device configuration mapped to memory. 4 kilobyte mapped to each device for each device. There are two types of interconnects, two types of components. One is interconnect, one is device. You see, if you see this diagram, this is one type of device. If you see this another type of device, interconnect is one type and device is another type, right? So interconnect is called as type 1, device is called as type 0, because the same architecture, again I may have one more interconnect like this somewhere here. This is another interconnect. So how do I differentiate this and this? This I will call it as type 0, this I will call it as a type 1. All of them are devices only. One is type 0, one is type 1. Okay, configuration space is a mix of fields, few hard coded and few configured by the processor. What is configuration space? I'll tell you exactly. Device configuration memory configuration mapped to a memory. Let's try to understand this keyword. What is meant by configuration space? In any device, what is configuration space is, let's say example, I am manufacturing a printer. I am a company, I represent a company manufacturing printers. Now I am selling the printer. I sell the printer. Someone purchases and uses. Someone connects that to their laptop, their PC or laptop, whatever. Now, as soon as you connect, these are two different units, right? Laptop is PC is a different unit. Printer is a different unit. So, how does my laptop, how does my PC, personal computer, get to know information about the device connected? See, I know that it's a printer. Does laptop know that it's a printer? As soon as I connect, does laptop know that the user has connected a printer and everything? No, it doesn't know. How does it get? So the first thing in PCI, it reads, the master in the case, the PC reads the configuration information present in the printer to get all the information. This is a mechanism where I read all the information. That will be standard. As a manufacturer, I will give configuration information. So I will provide configuration header. as part of my device. As soon as I connect my device into the system, that what my system will do is it reads the configuration header. That header will tell what this device is about. Is it a printer? Is it a music player? I'm just giving an example. What version of PCI does it work on? What is the type of device is it? Is it a device or is it an interconnect? What is the size of the memory inside the device? Everything it tells me, everything. That is what we call as configuration header. Why the term configuration? It is telling the information about the printer configuration. I mean, what is this printer is about, how it works, everything it is telling. That's why we are calling it as configuration header. So more about configuration header, I will explain you as we go forward. Any PCI device you take, everything will have a concept called as configuration header. The very first thing that happens when I insert my device into the laptop or any system is that system goes and reads that configuration header information to get all the details about the device. Next. So as I would say, rather I would say PCI feature summary. That would be appropriate statement. PCI, okay, it's not PCI Express. We are still in the PCI only. Next. Okay. Now talking about the features. I mean, just now we are done with PCI. When we talk about features, basically, I told you that PCI Express is a universal protocol because it supports all kind of features. I mean, if you take any protocol, right? If you take AXI protocol, AHP protocol, OCP protocol, if you summarize all the protocol features, this is what you will see. AXI supports out of order, overlapping, cacheable, bufferable, wrapping, incrementing, locked, exclusive, snoop, burst transfer, system diagnosis, full bus mastering, aligned transactions, unaligned transactions, support for messaging, sending the sideband messaging, sideband signals, interrupt support, error reporting, split transactions, retry transaction, the concept of cache coherency. These are the various features you come across in different protocols. Now, PCI Express kind of supports most of these features. What is that I wanted to tell in this slide is that different features you come across in different protocols. PCI Express as a universal protocol kind of supports most of the features that you see here. Okay. What is full bus mastering? We have already discussed. Ability of any of the connected component to act as a bus master. Every component has DMA to support this feature. DMA stands for what? Direct memory access. Which without processor intervention, it can read the data from some location and it can write the data to some location. That concept is what makes full bus mastering possible. If DMA is not there, then full bus mastering is not possible. PCI supports full bus mastering because there is a DMA inside it. What DMA does is, without processor having to read and write the data, it's the DMA which will read from a specific location, it will write to the specific location. That is how every component in that architecture can act like a master. What is the role of a processor in that case? Processor tells from where to read and where to write. Then what is meant by burst transfers? Address space done once only, doing multiple data phases corresponding to single address space. Since we are doing address space only once, data phases multiple times, we get better bus utilization. I mean, since you're sending the data multiple times, because effectively the data transfer is what gives you the bandwidth, right? Address doesn't give you the bandwidth. Address is only to tell where you want to transfer. It is the data which gives you bandwidth. So since you are able to do multiple data transfers, you get better bus utilization. So hence better bandwidth. For any protocol in VLSI industry, burst transfer is compulsory to get better performance. Any protocol that doesn't support burst will be low performance protocol. For example, APB doesn't support burst, so it's a low performance protocol. AXI supports burst, so it's a high performance protocol. So similarly, I can't say that PCI Express has burst. In PCIe, you can send packets which are having huge amount of data, because burst transfer keyword is more applicable to on-chip protocols. For serial protocols, that concept of burst transfer doesn't hold much significance. The term doesn't hold significance. Next. Then we discussed about PCI interconnect load, right? What is load means? PCI based interconnect supports connecting maximum of 5 components per interconnect. In connecting many components to a single interconnect increases the load of the interconnect. As the load in VLSI terms, it is the capacitance. Load means what? Capacitance in terms in VLSI increases. The time taken to charge the capacitor increases. Same port needs to provide increased amount of current to all the connected devices, because when you connect multiple devices at the output, you need to provide lot more amount of current. To provide more amount of current, you need to charge more. My capacitor needs to hold more charge. To provide larger current, it needs large amount of charge. To store large amount of charge, you need larger capacitance. As capacitance increases, charging takes more time, so hence the signal behavior degrades. As the capacitor charging time increases, the quality of signal decreases. So effectively, as in PCI, as the load increases, the performance degrades. So what is the summary? Uh, One port driving, in summary, what is summary you take out of this slide? Is that uh, it is a drawback. Summary is what? One port driving multiple devices is a problem, an issue, right? Because it degrades the signal behavior. So PCI Express doesn't take this feature. PCIe Express doesn't take this feature. Rather, what it does is it moves to point connection. What is meant by point-to-point connection model is, instead of connecting one port to multiple devices, you connect only one port to another port. That's it. How it is work, then how can we do all the connections? We'll discuss as we go forward. Next, PCI arbitration. Why PCI requires arbitration? See, many peripherals are connected to the same interconnect. All of them might want to do transfer at the same time, but only one of them can do, right? So arbitration helps decide which component initiates the transaction. That is where arbitration is required. So how? I think we are actually, there's a little order difference here. This slide is here. This one. Just take this one. I'm moving to a different topic altogether. Yeah. So the protocol features basically in general, not specific to PCI Express. So these are the protocol features. If you see any protocol features, so the question comes, how PCI Express supports. See, in case of on-chip protocols, there is a dedicated signals to support each and every feature. In case of PCI Express, as I told you before, PCI Express has something called as TLP header, transaction layer packet header. Uh, PCI Express uses various types of packets to implement these features, like DLLP order set. Through these fields, it will tell various information like traffic class, attributes, the packet poison, byte enable, virtual channel number, order set number, everything. For now, I would suggest let's not get into it. Just remember that everything happens through TLP. In fact, this might be even more confusing. Let's remove altogether this point. It should be sufficient. Because since you don't know what is attribute, since you don't know what is traffic class, since you don't know what is meant by EP, you will tend to get confused. Only thing you need to understand is TLP header has a field through which it supports all the features. That much should be sufficient for us. Next, how PCI Express has evolved. PCI Express takes the best of features from various protocols. Whatever is available, good things in each protocol, it takes that. For example, OCP supports out-of-order transactions by using thread and ID. Okay, if you see in OCP protocol, there is something called as Open Core protocol is there. It supports out-of-order transactions by using a concept called as thread and an ID. PCI Express also uses the concept of tag and ID. If you go to PCI Express, it supports out of order transaction by using the concept of tag and ID. PCI supports full bus mastering, which allows any component of interconnect to communicate with any other component on the interconnect. PCI Express takes this concept from PCI. This is implemented using DMA implemented as part of every device. So the point is what? It is taking the best of the features. See, from OCP, it's taking thread and ID. From PCI Express, it's PCI, it's taking the concept of full bus mastering. Concept of configuration headers is taken from PCI. Okay. Enumeration, address mapping, everything is taken from PCI. See, some features taken from PCI, some features from OCP, some features from some other protocol. Eventually, by mixing that, you have got PCI Express. PCI Express takes the concept of point-to-point connection from PCIe protocol. There is a PCIe protocol. From there, it takes the concept of point-to-point connection. Majorly, PCI Express has evolved from PCI and PCIe. PCI and PCIe are parallel communication protocol. PCI Express is a peripheral communication protocol. And in both these protocols, the problem was what? The problem is with parallel communication. That was limiting the frequency of their operation. To solve that problem itself, they moved to serial communication. Instead of parallel, they moved to serial. So maybe making a statement that it's parallel is wrong. I would rather say serial communication protocol, because it converts the communication model to serial nature, so that you can work at any frequency. That frequency limitation and clock will not become a limitation for you. Next, how PCI Express differs from PCI. That we have seen commonalities. Now let's talk about differences. One question is, if you ask me, do I really need to learn deep into PCI? Answer is no. Even if you don't have any knowledge of PCI, you can still learn PCI Express. Now, if you ask me, why am I teaching all these things when we don't really need? I'm just putting the foundation so that you understand how PCI Express has actually evolved. That's all. Okay. Uh, One difference is what? PCI is parallel communication protocol and PCI Express is serial protocol. PCI communication happens using transactions, which involves address space and data phases. PCI Express communication happens using packets. There we use TLPs, DLLPs, and order sets. You can say PCI is very similar to AHP protocol. There also arbitration happens. There also use send address and data. Here also same thing. PCI only supports IO transactions. PCI sees whole address space as a IO mapped address space. Everything it sees like IO space only, input outputs only. PCI Express sees whole address space as a memory mapped address space. For it, everything is a memory mapped space. PCI maximum bandwidth you can get is 533 megabytes per second, working at 133 megahertz. See, while we are running a clock at 133 megahertz, the maximum bandwidth you get is 533 megabytes per second. For PCIx, that's the intermediary between PCI and PCI Express. PCIx gives a maximum bandwidth of 4262 megabytes per second. That is majorly because this frequency has been increased here. Means when you come to PCI Express, you are able to run it at higher frequency. I think 8 times, maybe 1 gigahertz or something, or maybe the bus width they would have doubled. See, this would have been working at 512 megahertz, and the bus width would have doubled, effectively increasing it by 8 times. 4 times here, 2 times due to bus width increase. Okay, PCI and PCIx bandwidth is limited by their architecture. Basically, inherent disadvantage is due to parallel nature of communication. Means when it is parallel, that's a limitation. That's all. I mean, you cannot do anything because you cannot really meet the setup and hold time with clock sent parallelly. And the second limitation is due to fan out. Load capacitance limits the frequency of operation and signal behavior gets impacted. These are the problems with PCI and PCIx. This is what PCI Express addresses in the PCI Express protocol. PCI Express topology is backward compatible with PCI. What is meant by that? Okay. What is meant by backward compatibility? Let's try to understand. By now we know that PCI Express has evolved as a advanced version of, as a replacement for PCI and PCIx. Now the question is, there would have been thousands or lakhs of devices, lakhs of systems which are developed to work for PCI and PCIx, right? Let's say, take today. Assume that around 1990, 1995, there may be 1 lakh devices, systems which work, which support PCI and PCIx. But then now what happened is, in 1996, Express Gen 1 award, for example, okay, I'm just taking example, and I manufacture a device, a PCI Express based device. If I cannot connect into these systems, it's a problem, right? If I cannot, if I'm, there is no flexibility for me to connect PCI Express based device into this, then there is no problem. I cannot ask these 1 lakh people to change their system to PCI Express immediately. So that is where you need a backward compatibility, where I should be able to connect. I should be able to connect PCIe device into PCI slots. So, uh, so as I said before, one of the problem with PCI was what? Parallel communication. So PCI Express protocol is changed to serial type to solve that problem. Second was what? Multiple components connected using interconnect was a problem. So what PCI Express does? PCI Express moves to a point-to-point connection model to reduce that problem. If some protocol is point-to-point, then there is no load or no impact on capacitance, right? There is no problem of load itself in that case. Hence, we get best possible signal integrity, signal behavior. So there were two major problems. One is with parallel communication. One is with the multiple components using the interconnect, connected to interconnect. That was impacting the signal integrity. So PCI Express solves the both problem. One is by moving to serial nature. One is to moving to point connection model. Next, PCI Express maintains backward compatibility with the PCI. One is hardware backward compatible, ability for connecting PCI device into PCI Express based architecture, as vice versa. Second is what? Software backward compatible. Address mapping, configuration headers, and enumeration concepts are same. PCI uses same concepts. PCI Express also uses same concepts. And PCI Express supports the PCIe transaction, whatever IO transaction. See, in PCI we use what? IO transactions. PCI Express also supports them. If you read PCI Express currently, Gen 3, Gen 4, everything, they will have IO transactions. They are kept purely to support PCI. Otherwise, IO is not required at all. Meaning, when you read the PCI Express specification, you will come across some type of TLPs called as IO write and IO read. It is only for supporting PCI, only for backward compatibility. If that was not the case, then PCI Express don't need IO at all. It could just manage with memory writes and memory reads itself. Next, why backward compatibility is required? I told you, right? The reason why it's required. There are many devices and applications developed based on PCI topology. If PCI Express doesn't support PCI based hardware and software features, then all those things can't be connected to PCI Express topology. It will be a big limitation for anyone moving from PCI to PCI Express topology. Hence, PCI Express maintains backward compatibility. That is the reason you see PCI uses IO based transactions. PCI Express is based on memory based transactions. See, PCI works on IO based transaction. PCI Express is memory based transaction. But again, to maintain backward compatibility, PCI Express implements IO write and IO read type of transactions also, just to make sure that PCI based transactions also support PCI. Means it takes all the best features. It also make sure that the backward compatibility is not lost in this process. I think we have already talked about what is parallel communication protocol and what is the drawbacks. See, parallel communication protocol, what are the drawbacks? Signal skew is a problem. Clock skew is a problem. Flight time is a problem. Next, PCI Express addresses these limitations of parallel protocol. How? It makes the protocol serial in nature. If you make the protocol serial in nature, there is no problem of data skew won't be there. It removes the clock signal between the two connected components altogether. What is mean by that? If you remove the clock signal, there is no clock skew also. How it can work without clock? It is a synchronous protocol. Is it asynchronous protocol? No. Thing is, clock is embedded into the data pattern itself. Receiving device can extract the clock out of the data pattern. How it takes care of flight time? PCI Express uses 5 component which ensures that all data is collected in proper manner. It uses concept of data buffer which avoids the issue of flight time. There is a data buffer. Because of that, whatever rate data comes, it doesn't matter. You don't need to process. You store it into a data buffer and you give it to the upper layer. So you don't have to worry about how much time does it take for the signal to go and you need to respond back. Once these issues are addressed, everything is good about PCI Express. I mean, it addresses these issues, so that makes PCI Express a very high efficient protocol. Next, we were discussing about PCI Express configuration space. Let us quickly talk about what is configuration space. I think let's talk about configuration space later because I don't want to introduce right away. Let's directly go to PCI Express protocol summary. In summary, it takes all the important features of PCI and PCIX, like full bus mastering, point-to-point communication. It uses a bridge for connecting